This is my mathematical tech talk presentation video. In this video I am going to explain application of partial differentiation. So here tangent planes and linear approximations. Suppose a surface S has equation z is equal to f of x comma y, where f has continuous first partial derivatives, and let p of x suffix 0 comma y suffix 0 comma z suffix 0 be a point on S. Let C1 and C2 be to the two curves obtained by intersection the vertical planes y is equal to y suffix 0 and x is equal to x suffix 0 with the surface. Thus, point P lies on both C1 and C2. Let T1 and T2 be the tangent lines to the curves C1 and C2 at point P, then the tangent plane to surface S at point P is defined to be the plane that contains both tangent lines T1 and T2. Here, suppose a surface S has equation z is equal to, see here, z is equal to f of x comma y, where f has continuous first partial derivatives x suffix 0, y suffix 0, z suffix 0 be a point on S. We know from equation, we know form equation that any plane passing through the point P of x suffix 0, y suffix 0, z suffix 0 has an equation of the form. See here, the form is here. Z minus z suffix 0 is equal to fx of x suffix 0, y suffix 0 into x minus x suffix 0, x plus fy of x suffix 0, y suffix 0 into y minus y suffix 0. Next one is linear approximation and line horizon. So here the line horizon of f at a comma b is a linear function whose graph is the tangent plane, namely here c L of x comma y is equal to f of a comma b plus fx of a comma b into x minus a plus fy of a comma b into y minus b. The approximation f of x comma y, f of a comma b plus fx of a comma b into x minus a plus fy of a comma b into y minus b is called the linear approximation or tangent plane approximation of f at a comma b. Next one, see here. Recall that delta x and delta y are increments of x comma y respectively. If z is equal to f of xy is a function of the variables, then delta z, the increment of z, is defined to be delta z is equal to f of x plus delta x comma y plus delta y minus f of xy. If z is equal to f of xy, then f is differentiable at a comma b if delta z can be expressed in the form where e1 and e2 is equal to 0, as delta x delta y is equal to 0 comma 0. Next one is theorem. If the partial derivatives fx and fy exist near a comma b and are continuous at a comma b, then f is differentiable at a comma b. For a differentiable function of two variables z is equal to f x comma y, we define the differential dx and dy to be independent variables, then the differential dz, also called the total differential, is denoted by dz is equal f of x, dz is equal fx of a comma b dx plus fy a comma b dy is equal dou z by dou x dx plus dou z by dou y. Here, see here. For function of three variables, w is equal to f of x comma y comma z. First one is the linear approximation at a comma b comma c is f of, see here, x comma y comma z is equal to f of a comma b comma c plus f of x a comma b comma c into x minus a plus fy of a comma b comma c into y minus b plus fz of a comma b comma c into z minus c. Second, the increment of w is delta w is equal to f of x plus delta x comma y plus delta y comma z plus delta z minus f of x comma y comma z. Third is the differential dw is equal to dou w by dou x dx plus dou w by dou y dy plus dou w by dou z dz. Okay.